Thank you. And as a way of, I guess, warning, apology, something, I have about twice as many slides this time as last time. So I'm certainly still happy for discussion and questions, but I will try to keep on the pace of getting through this in the time we have. Secondly, there is a bit more technical discussion of a specific definition. I felt it was important because the concept it's expressing is really important. And so it is worth digging into like what this definition actually means and unpacking it, not only for MAIDs, but for more general modeling type questions. So I'm going to advertise that I'm trying here to do a barbell strategy. This is an idea due to Nassim Taleb, that you try to hit two extremes at the same time. And by doing so, you're likely to capture at least one of them in a useful way. So here, the two ends of the barbell, the two extremes that I'm hoping to connect while still hitting both sides adequately, would be that there are practical considerations here that could potentially be used to make coding more effective in whatever way one defines that, of coding simulations more quickly, more reliably, with greater translation between different models, however one defines that. I have some ideas that I think would be practical suggestions of things to consider for that. And then also, there's a lot of theoretical math, both within the paper and that is sort of implicitly suggested by the paper, especially when it comes to putting the idea of connections between different fields on a rigorous footing. So the first thing I would say here is to review what MAIDs are, because it has been several weeks since we last discussed them. MAIDs are diagrammatic models of multi-stage games. And through these diagrams, they encode the agents who are playing the game, the state variables that are relevant to those agents, the decision rules that those agents are utilizing when they are making decisions at each stage of the game, as well as random chance processes that emerge, that are utilized or occur within the game. And finally, the utilities, which will be essentially a calculation of how satisfied each agent is at the end of the game with the outcome. And this is a well-known idea from broader economics of a utility function associated to an individual that assigns a way of quantifying or representing their outcome and how satisfied they are with it. The specific scenario that we worked through and are not going to abandon is this killer tree scenario, which involves two players. So we have Alice, who is represented in orange, and we have Bob, who is represented in green. And it's sort of a tragedy that Alice really wants a patio that she can see very clearly from, but there's a tree that blocks her view. And Bob loves the tree and wants to keep it. And Alice may be willing to poison the tree to get it out of the way to improve her view. And Bob maybe, will take defensive action. Now, what's important to realize here is that Alice's decision to poison the tree is not something that Bob knows about. And so it's not something that is relevant to the decision. However, Alice's knowledge of whether she poisoned the tree or not is information that she can consider. And so information that can be considered when making a decision is observable information, as represented by this dotted arrow that an agent would be aware of when they need to make a decision or could access at some level. And then there's also the controllable variables, which are things that are direct influence of one variable on another. And so, for instance, here, if Bob decides to call the tree doctor, that will incur a specific cost that will be one of his utilities. On the other hand, if Bob sees the tree become sick, then he will take that knowledge into consideration. He still may or may not decide to call the doctor. And so that's the difference between the direct influence of controllability and just the information availability of observability. And so that's the framework that we're looking within. Does that seem familiar and or understandable to everyone who was here last time or is here now?
Yep, that makes sense based on last time.
So, but actually, this isn't quite a MAID yet. There's important information. This might be called like the structure of the MAID or the graph of the MAID, but it's not a MAID. There's important information that's missing in terms of how the players actually play the game. And the three things that we're missing for decision variables, we need a decision rule of, given this information, the player actually has to decide what to do. Given the fact that the tree is sick, Bob has to decide whether or not to call the tree doctor. That's some type of computation or rule that's followed based on the available information. So it may be that Bob, is tired of the tree anyway and is only going to call a doctor 10% of the time or 0% of the time. There are other considerations, like it may be that he's only going to call the tree doctor if it costs less than this much, potentially, which is not currently something we see in the information flow, but could potentially be part of a decision rule. And the decision rule is something that each player would need to have before we could actually play the game in a way that didn't require human participation. The second thing is that a chance variable, when we're randomly deciding, essentially nature or the system is making these decisions rather than agents within the system. For instance, if the tree is poisoned, does it become sick? Maybe the poison didn't work. Maybe the tree is very hardy and just isn't affected by the poison. There has to be some way of processing the information of the tree was poisoned or not, and then turning it into the tree is sick or not. And for things that aren't agent decisions, that might be more reasonable to represent this as a conditional probability distribution. Now, something that I think is important to emphasize here is that these are not mutually exclusive. A conditional probability distribution could actually be a special type of decision rule that is applied. Maybe, Alice flips a coin to decide whether or not to build the patio. But it is the case that it's worth distinguishing them at sort of a philosophical level to emphasize the agency in making the decision versus this is just something that happened that was outside of anyone's control. It's a natural or systemic property. So as a specific example of what a decision rule would look like, these assign values to variables, and only once at a particular stage in the game. And so I was reflecting on some of the discussions we had in the first session about the differences and commonalities between GDSs and MAIDs. And I realized that this actually is worth distinguishing a bit or highlighting that this is a distinction. A GDS will typically start with an initial state where all of the values are set. And then through the admissible actions, it evolves into another state. Whereas in a MAID, there's a sense in which we're thinking about these values as not being assigned or as being unknown until the agent action is taken. And maybe it's possible that there's a distinction without a difference, or that there is some workaround, to make those things compatible. But it actually is a difference that there's no sort of default value in a MAID where it starts out with this and then gets changed. It's that we might think of it as the value is not set or not known. And that's going to become important in a few moments when we think about conditional probability and information flow within these different types of structures. In terms of thinking about these things, from a structural level and how we actually would implement one at the level of, concrete calculations, the rules here are going to depend on parents, or more generally predecessors, in terms of the information that is available. So a parent of these aren't quite the same thing. A parent is like an immediate predecessor. So a parent of a vertex or a node is a vertex that has a directed edge to that node. So here we would have that poison tree is a parent of build patio. And it's a very intuitive relationship to see, especially if you think of it like a family tree, which is where the nomenclature comes from. So that is the review of MAIDS, kind of like a quick recap of where we started and now back to what we would need to know in terms of absolute essentials for the rest of the discussion. Are there any quick questions or thoughts before we move on to the next stage of this?
So I'll make an observation and you can say whether or not it's helpful for you or anybody else, but thanks to Danilo and some others, I tend to think about the relationship in terms of, I guess, sort of passing through something like Bayesian networks. Like MAIDS is like what happens when you take something like Bayesian networks and try to move in the direction of a game or a dynamical system. And I think, at least in my experience, we more started with GDS and cadCAD from the perspective of things that are kind of fully dynamic, and then worked towards how different kinds of network structures over the computation work. So it starts from the extreme of the abstraction of a dynamical system, and then works to give it structure and flavor and color. Whereas I view MAIDS as kind of coming from the other direction, starting with something closer to Bayesian networks. And I don't know if this matches with your experience or with Danilo's, but obviously there's just a big family of different systems modeling abstractions, and we want to have facility with many, and that understanding to some extent their relationship to each other can help with tool selection.
So if I capture this correctly, you're saying GDS is like the more abstract, most abstract, potentially high-level view, and then you instantiate that with specific models, whereas Bayesian networks are more concrete, and then you start to generalize them, and MAIDS maybe meet somewhere in the middle.
It's more that GDS is just, and I would even dropping the G, just saying like starting from dynamical systems and working from there, and like asking what we can learn from a dynamical system as the sort of starting point, and then working towards the problems that we're actually solving. Whereas and again, GDS coming from DS and being applied and factored and structured into block diagrams and various structures that we use, is like a path, like from dynamical systems to our problems. Whereas I view MAIDS as coming from the Bayesian network as opposed to the dynamical system as its sort of like prior art. And then they both work towards the middle, which is real world problems that we're trying to solve, and they have some similarities with each other. But if I were to kind of linearize, for lack of a better term, at one extreme there's dynamical systems, at the other extreme there's Bayesian networks, and then as you creep from those ends towards practical applied problems, you'll move through these what I'll call applied abstractions, and that our GDS models as well as MAIDS are applied abstractions for specific problems. And they have things in common because they're working towards, again, like concrete design and analysis problems from the more abstract mathematical object starting points.
That makes sense to me.
Yeah, if I can add something very short, I would like you to continue, of course. So it just seems to me that in the bidirectional network you have, or at least an example that you showed, you kind of have already like the states of the game somehow defined, right? Whereas in let's say fully stochastic problem, those states may be so large and depend on the randomness that we may not have those states explicitly, in the network itself because it'd be so large. So I guess that I'm just wondering how scalable are those, is this technique, for example, for real world problems? How would you address something like that?
This is always a challenge. Like with statistical physics, are you tracking the position and velocity of each particle, or are you just fuzzing out and looking at this is solid or gas? Because I think the question is about how much the homogeneity of the agents matters. Because if we had like 10 copies of Alice and 10 copies of Bob who are all playing interdependent games, even 10,000 copies of Alice and 10,000 copies of Bob. At some point, it might make sense to use something like a, fuzz out mean field approximation. It's like, oh, there's really only one Alice, and then probabilistically, we're collectivizing it back to this high level abstraction.
Like how would we compute a solution to this small example? Mathematically speaking, what would we do? Just compute the conditional probability of every, like from the bottom to the top?
What would computing a solution mean here?
What is the strategy that either Bob or Alice should take?
Yeah, it's a function of the statistics of the random variables and of the parameters of the objectives. So I think the first thing is, I don't know that Octopus has prepared for, nor I'm necessarily didn't ask for this, but the analytical classes of solutions for MAIDs, I think, are in some of the MAIDs literature that were shared. I don't know them offhand, but I believe they're closely related to work with Bayesian nets, which is part of the reason why I brought it up. The point that I think was substantive in your first question, though, is about model scoping, right? The models themselves don't come like ex nihilo. You're in an engineering process, you're choosing your model, your representation. And so that's part of the reason why I talk about it in terms of tool selection, right? When you hone your model and figure out what to fuzz in, what to fuzz out, you're picking both a class of models, whether it's, say more GDS or more MAIDS oriented. You're picking, whether you're doing something, expecting a model that can handle analytic techniques versus one that's going to be predominantly simulation based. Looking at what questions you need to ask and answer is usually the more important step in model selection. So, if we're dealing with a population level problem, then likely we're going to use subpopulations, not individual agents. And that might affect whether we want to represent the problem as a MAID or something else. Though, to the earlier point, you can actually represent a decision as the aggregate behavior of a subpopulation and still use a MAID model if that's suitable for the problem at hand. But I think, and I'll let this be maybe the end to move back into the talk, is it's just important to remember we're doing these sessions to give people instincts for model selection. It's not you should use MAIDs. It's here's what MAIDs and some of the other concepts that we use are good at, how they work. And so that you can decide when or whether to use them in a project. And like time and time again, this is going to be my main criticism of a lot of the economic game theory literature, is that it's actually disconnected from that practice. So I like the control theory, more kind of, I guess, defense funded branch of game theory, because it's always been tied to specific problems. And so you get more bespoke solutions, but they come equipped with a bit more, here's how we picked the model, why we picked that model, and how it performs in the application it was developed for, rather than a kind of universal theory of, again, something. So I'm going to give the floor back, but I think your questions are all valid, and I think we should think about the question of whether something's analytically tractable or not as one of the model selection criteria, or like tool selection criteria.
Thank you.
This is going to be one of the things we return to in the next talk in this series, because I think one of the things one does in a traditional dynamical system lots of times is try to find equilibrium points either through analytic solutions of a fixed point equation or simulating and hoping that if you start with the right initial conditions, you'll hit the attracting fixed points. And I think, although I'm not a game theorist, but there are algorithms for solving what the equilibrium of such a thing would be. And how those scale, I'm not exactly certain, but it does exist and we can discuss it. Okay, so the MAIDs are a generalization of a thing called influence diagrams. Essentially, a MAID, you can view this in two different ways. You can view a MAID as a generalization that adds some information to an influence diagram, or conversely, you can think of an influence diagram as a restricted type of MAID. So if we're thinking of an influence diagram, it's a MAID with only one agent, but it has all of the other information that MAIDs have. In particular, there would be chance processes and decision rules. And so, to what Dr. Zargham said, I'm trying to get out of this talk and all of my talks without giving the precise mathematical definition of what a category is. But let's just say categories are classes of mathematical objects that share similar structural properties. So, and what's interesting is when we translate between these things, it can reveal information and we can be consciously choosing to add or forget certain information. And the idea of a category brings both rigor and compositionality to that idea that we might be moving around in similar mathematical spaces. So influence diagrams would be a subcategory of multi-agent influence diagrams. You could also view them as separate things, in which case you could think of having an arrow, what's called, I hate the term functor, but it's what's used. Forgetful functor from the category of MAIDs to the category of influence diagrams, which would be that you simply forget that there are separate agents and you treat everything as if it is one agent who is making all of the decisions and don't have any competing interests. It's not perfect. I don't know if like this is something I discussed with Dr. Shorish, how to make this precise and maybe some obstructions to it. But at the very least, at the beginning, it's a high-level thing of, okay, if I'm working with a MAID, I could forget that the agents are separate people, and I could just kick back to an influence diagram, potentially. Carlina, I see you have your hand up.
Yeah, sorry for that. I just very quick question, maybe a bit silly, but so if you now only have one agent and there are no competing interests, then what is the goal here then of the game? Just to compute the best decision given the randomness?
So if there are two kind of potential ways that you might try to attack this. One is you could it's like, what do you do with the utilities here? If you forget that the different agents exist, then the different agent utilities go away. And one thing is you could just forget them. So you could assume the agents are making all decisions according to some specific decision rules and specific probability distributions. And then you could get things like this, computationally, this would occur this proportion of the time under these conditions. And it's sort of an initial space mapping technique that we're not worried yet about utilities, but if people made decisions completely randomly, if people made decisions according to these simple rules that we plugged in, and then we assume these probability distributions, what does that look like? It is a simplification technique to, maybe I don't understand the problem at this level. Can I understand it at this level? The other reasonable approach, in my opinion, would be to try to combine them and think, now we're looking at community welfare. And total welfare of the system should be some type of computed thing that comes from the combined information of the different individual agents, but we're going to absorb those different trade-offs into one overall system objective. And in that case, this is definitely more an art than a science. It's all kinds of different control theory, machine learning, generally speaking, optimization problems that you have different objectives. How do you combine them? And there's no right answer. There are reasonable approaches, but the right one doesn't exist. So if we took this one, you could define the mapping and just say, okay, we're deleting all utilities, and we now have a different model. If you're doing this one, then it would come along with a specific choice of, we always combine individual utilities into a collective utility into this way. And it's not a matter of, both of them are possible choices that would give a different perspective. The goal here is to sort of have a map of the models that we can say, we are in this part of modeling space, but we want to go over here. What are some reasonable ways that we could get from this part of modeling space to here? And recognizing that sometimes that's a human primate cognitive thing, and then we're trying to give rigor to it with a mathematical perspective, but it's not always possible. We are in both domains at the same time. So maybe let me try a heuristic. If I hit something and I'm not sure what to do with it, okay, I don't want to be stuck. That's like, being stuck is not good. So what I want to do then is think, okay, what else could I translate this to that I understand better, that can then give me a scaffolding for coming back to the original problem? And that's a problem solving like techniques that we all pick up informally. What category theory has the ability to do is to make that precise. Say, okay, this would require a lot more work to make precise at the level that it might be useful. But you say, okay, I'm moving from a MAID to an influence diagram. Let me figure out something about the influence diagram. And then if I have sufficient understanding of these two structures, I can know more exactly which compromises I'm making, which information I'm losing, and how I could be able to translate it back. And the second thing is just as a mental model of thinking, okay, this model isn't working, or this model is too complex for the effort that I currently have available. I'm going to kick down to the simpler model, but I'm making that decision very intentionally and recognizing, where am I currently, where am I going to, and which information am I willing to lose in that process? Does that make sense?
I think so. Thank you. Yes.
Thank you. I really appreciate everyone's questions. Lots of things y'all are asking and saying are things that I'm getting to later, so they will, like, I can just jump ahead and don't have to worry about getting through slides. But a forgetful functor forgets some information, and in doing so, you're losing some structure, and the hope is that the structure I lost is worth the simplification of maybe being in an easier to understand world. And those mathematical worlds are represented through these types of categories with arrows between them.
I dropped a link to this, but my go-to hack when I'm trying to resolve something in category theory is to ask chatbot questions that amount to explain it to me like it's linear algebra, which is obviously not a perfect match, but like I know my linear algebra really well. So when I say how is this like this linear algebra thing, then it explains to me how it's similar and different to that idea. And then I actually build a connection in my mind to things that I know, again, in a much more, like, I've spent many years working with real analysis and linear algebra. So when I ask it by comparison to things I know, it makes it much easier to hook into my existing mathematical knowledge.
I'm really happy that you said that, because it's totally orthogonal to how I do it. So I guess I do it with abstract algebra and topology. which is, I guess, what I'm more comfortable with. So it's like whatever you are, okay, maybe that's the point. Everyone has some categories they're comfortable with, right? And they understand how information would move within that category. Like for me, it's algebraic structures like groups and rings, because I'm a cryptographer at heart. And for you, it's linear algebra and real analysis. So you understand like
Linear algebra, real analysis, dynamical systems, and actually graph theory, and I think that's where we intersect, right? Because that's where the topology and the algebraic structures intersect at the algebraic graph theory and like higher order algebraic representations like simplicial complexes. But your point, you nailed it. I'm not saying you have to use linear algebra. I'm saying use what you know.
Yeah. So whatever, like every one of us has a category we're an expert in, and then we can use that to understand categories in general.
I do sometimes joke that like my understanding of category theory has come to be like a black hole, like black holes or like wormholes in math space, where you can like use it to teleport from like a seemingly distant region of mathematical modeling space to something else, and like actually forging an understanding of the relationships between the objects. That's like what category theory is actually really good at. It doesn't actually do anything better than just doing that thing. It's when you have to cross, when you have to jump. It's your like kind of super highway for connecting mathematical concepts.
It's like that scene in The Matrix where he's like, I know Kung Fu. And it's just been downloaded into him. It's kind of like, you know, a person in an educational math with sufficient math education has expertise in at least one category, whether it's vector spaces, groups, rings, topological spaces, whatever. And then you get sufficiently deep knowledge and you get category theory, just like it's a metaphor, right? You're like, oh yeah, it works this way because, and then I translate it over immediately. So someone can tell you this is like this. The category theory is like a language of metaphors between different types of math. And sometimes that metaphor is, you know, dropping specific information. If you say a lizard is an animal, that's not wrong. It's just changing the level at which you're looking at it. And so that may be helpful or not, depending on the specific thing that you're trying to figure out, which gets back to Dr. Zargham's point that these are about specific questions and specific real world problems. And that's the goal of this, is not to make it abstract, except to the degree that that level of indirection actually assists in getting somewhere we want to go in the space of real world engineering problems.
And Danilo and Jacob have been working on, I think, a piece which I hope will come out sometime in the not too distant future about complexity management in models, which speaks a little bit more to when you have specific questions in mind, how do you think about tuning your models, your choices of what's in and not in, or what's dropped or kept with your mathematical model, like selection, to Octopus's point, how that relates to like an engineering project and engineering process. So if either of them are on, they're welcome to chime in, and then we should probably keep going.
Yeah, this is a piece that probably I'm going to ask feedback from the channels soon. But I think that a large deal of our work is doing what Z calls reverse engineering requirements, in the sense that we want to get a well-suited understanding of the phenomena that's happening, but also the questions being asked about that phenomena. Because there is a diagram that I like a lot that essentially does a taxonomy of model paradigms across 3 dimensions: the spatial dimension, the temporal dimension, and the topological dimension. And the reason why I'm saying that is because, for example, when we are trying to, let me see how I can make the link here. I think that MAIDS has a high value because, I mean, we do have our toolkit of modeling. I think that our toolkit for dealing with population, superpopulation like models, which typically speak the time scale is like 1 day or 1 hour, is quite robust. There is a lot of literature on econometrics about that. But I think that MAIDS can help a lot to us to have a better toolkit to understand how to approach granular models, the ones that deals with agents, but also when we deal with agents, we can also think that each subpopulation can also be understood as a giant agent. So yeah, just providing some items there that could use for discuss, but yeah, I don't have anything too specific to chime in now.
Thanks, everyone. I love these discussions, and I wish almost there could be like 2 sessions, one on direct presentation and one on just free-flowing discussion. And I guess the challenge of the moderator is to figure out how to let them flow. But that's not my job. I have to do that when I teach classes, and it's never fun to figure out how to balance those things. Okay, so this actually, these 2 different examples, in addition to being a what's the right approach, there isn't one, but they actually show 2 different types of transformations that you can have when you're making a conscious choice to transform one mathematical object into a different mathematical object for the purpose of potentially understanding the original object better. This first type, where I just delete the utilities, does not require any choice. It's a canonical thing. If I just say delete the utilities, that's perfectly understandable. This transformation does require a choice on the part of the modeler. Dr. Zargam has just informed me there is no moderator, which makes my anarchist heart very happy. This requires a choice of how we combine these things if we're not just going to get rid of them. This is actually like well defined because you can think of this as living in probably some type of vector space, like for the state variables, 5-dimensional real vector space would be perfectly reasonable with 5 variables. This is more like an embedding where the extra coordinates are having to be combined in some way. And this, again, the whole point here is you can do this basically automatically, where you just delete information. But if you're going to be creating new information, there has to be some level of choice about that new information is created. And those are 2 different ways of doing things that are not incompatible. It's just being conscious of which one we're doing. And so if you wanted to build from the influence diagram back up to the MAID, you would now not have you would need additional information to do it. You would need to separate which variables belong to which agents, which utilities belong to which agents. And this is actually the art of modeling, or one of the arts of modeling, in my view, is when you add this information and move up a level of complexity, how exactly are you doing it? One map that would be completely legitimate here and that would be automated would be an identity map, where you don't add any information. You just take the original influence diagram and don't add any information. But that's not what we want if we're actually trying to move between categories. So here is where human cognition is essential. So it might be helpful to know that in mathematics, this is often called a lift or a section. If you've taken a math class where those were used, you think about the first type of map as a projection, and the second type of map is a lift. There are different techniques where you project and then lift, or you lift and then project in a certain way. And then if that's a useful way for you to think about it, great. If not, let's pretend I never said it or discuss it later. So one thing that this might represent, if we're thinking about moving between different models in a structured way, either formally or just heuristically, this could represent that we are going from the system level view, which does not consider the interest of different agents, to the agent level view, which does. And this is the situation that occurs all the time when you're looking at a decentralized protocol, where potentially if every actor in the protocol was just a program doing exactly what it was told what to do, the protocol would work perfectly. In a decentralized protocol, we're asking individual agents to perform these roles that are not automatically performed mechanistically, but are chosen to be performed based on the utilities that are available. And so one reasonable way of thinking about the decentralization problems is, what if I made the decentralization go away? What if every US citizen were assigned a Bitcoin miner and told that they must mine Bitcoin? Then the system would work at some level. Whereas if it's an individual choice whether to have a Bitcoin miner and whether to mine Bitcoin, it becomes a very different problem. In some sense, the actions being undertaken are the same, but what is added on here is utilities. And what I'm trying to say is that making that step of adjusting the mental model corresponds exactly to this step in the modeling process of going from an influence diagram where there are no distinct agents and no distinct utilities to a multi-agent influence diagram where those things become essential. It's possible that this could be used to add rigorous criteria to something that we intuitively do. So maybe there are already like economic results of what happens when you go from central control to decentralization or vice versa. The only one I'm aware of that would be reasonably close is price of anarchy, but I'm not an economist by training, so it's possible there's way more here. But in terms of the modeling process, it seems like we run into this problem a lot. And so giving it a name, maybe, and giving it a sort of mental schematic is one way to think about it. Oh, we're moving from an influence diagram now to a MAIDS, or vice versa.
You're actually bumping up against, I think, a reasonably interesting class of problems around aggregative utilities. So a whole bunch of literature just on the ways in which you aggregate utilities of a bunch of distinct actors to form, a quote unquote global or social utility function. There's a post which I'll find in Slack that I pointed to someone constructing a family of those actually. But I think if anything, we're poking here at the sort of there's a sort of incompleteness, like a natural incompleteness at this point, where the moment that you go from a system as a whole thing to many distinct agents with agent utilities, you sort of imply the existence of a mapping, but from the agent utilities to some sort of global or aggregative utility. And actually the set of all possible mappings from the individual utility functions to the set of individual utility functions to some one utility function is really big. And it contains things that are qualitatively very different, and sometimes even qualitatively really different on non-obvious margins. Like just Rawls maximin versus summing something is like going to already create huge differences in implied structures, like what structures are good or bad. So anyway, that's a huge thread on its own, worth discussing in a future call probably.
Thank you. I will look forward to reading those. And discussing those. It's cool to learn more economics. I think too, from just like there are times in a modeling team where it may be important to reach consensus about a design decision, or it may be important. There, I mean, at the end of the day, decisions have to be made, actions have to be executed. But the more comprehensible those things are to the individual team members, can be helpful at times to those types of conversations. So this is something that this is a judgment, but I would say block science is really good at this, at giving a mechanism like a memorable descriptive name that is then easy to discuss. So in addition to the technical aspects of this, I also just want to propose conversational frameworks of, if I say, hey, I'm taking this from a MAID to an influence diagram, or vice versa, that is meaningful to people, and they at least have a high level idea of what's happening with, and then the details are also important. Does that make sense?
Yes.
Thank you. I guess I should be really clear. It's not my work. It's due to Collar and Milch, who I hope have success or sufficiently credited. I'm not sure I said that in this talk, so it's important. Okay, so here I'm just kind of beating the same point, so I'm going to move on from it. Maybe the one more thing is this idea of realism versus testability. So the even more testable model, which is still living in the category of MAIDs as a simpler type of MAID, is the Bayesian network, Bayesian network. And you can view this as a subclass of influence diagrams, where there's only one agent and where all variables are chance variables. Nothing is actually considered a responsive decision. So this is one of those things where I'm saying what I know to people who know way more in this term. So I'm going to give my perspective on it, and hopefully that's helpful, but also I'm happy to be further educated, especially on this one concept where I'm playing catch up. The key concepts that we want to get out of Bayesian networks, and I'm choosing Bayesian networks here because they're easier to understand without the additional information of MAIDs. But all of the concepts either have been translated or could easily be translated to these types of diagrams that contain more information. And the key concepts out of this discussion are conditional independence, directional separation, and designing versus fitting of models. So here's what the same model would look like as a Bayesian network. The idea here is no one is actually making a decision deterministically based on information. Everything is a random process. Now, that random process can still depend on information available from other random processes. In other words, there are still conditional relationships. So we need conditional probability distributions. And once we had conditional probability distributions, going back to Carolina's point, the things would still be, these would then be analytically tractable for some maybe small number of variables. Although, if I remember correctly, the analysis is quadratic. Yeah, it's at most quadratic. I believe it's big O in the number of edges. So that's at most quadratic in the number of vertices, which, especially if the model is relatively sparse in terms of these things, is tractable for solving computationally. So a single arbitrary assignment of conditional probability distributions would be for taking a variable, giving each possible value that variable could take, giving it a probability that it takes that variable. And then once the value of poison tree has been assigned, tree sick depends on whether the tree was poisoned or not. So this is conditioned on the value of the poisoned. And in this scenario, I've assumed that it's very unlikely that the tree becomes sick if it is poisoned, and very likely that it becomes sick if the tree was poisoned. Similarly, tree doctor is conditioned on the tree being sick, and you have the same kind of distribution here. And we actually need 5 of these, and the last 2 are larger. So taken together, all 5 of these conditional probability distributions, along with this graph, would correspond to, would actually define a Bayesian network. So one of the key concepts of Bayesian networks and that we want to illustrate here is conditional independence. And the definition is a little bit, it's a little bit formal here. But basically, if we have if we have 3 sets of nodes in a Bayesian network, and we want to discuss the relationships between them, we say that X is conditionally independent of Y given Z if for any Z variable which has non-zero probability, and for any choice of X and Y representative, we have that the observing Y does not change the probability of that X occurring. And I have the formula correct because I realized yesterday that I had written this incorrectly. And then I see that my verbal description is still incorrect. So let me correct this. My intuitive understanding of this, and I would actually appeal to Jamshid, Danilo, Zargam, or anyone else who feels comfortable verifying it, is that if we already know Z, if we want to know about X, or have a belief about X, and we already know about Z, then knowing about Y doesn't change anything in terms of what we expect out of X. That's what I would give as my intuitive reading of this based on the formula. And we're going to spend some time digging in here, because this actually took me a little bit of time to wrestle with until I felt I had intuitive understanding of it. So this is an important thing to know, is lots of times in modeling, we're thinking about direct causal influence. Like in a physics model, one ball hits another and it causes this ball. But this isn't about direct causal influence. This is about the observer's beliefs being updated as they get additional information about what has occurred. So it's possible for 2 things to not be conditionally independent, even though one doesn't directly cause the other. Like a future event, a past event can actually not be conditionally independent of a future event, even though we're not believing in retrocausation. But rather, observing that something happens today might inform us in a way that we now have different beliefs about what happened yesterday. That's the idea of something is conditionally independent, that information arrival does not change our beliefs. But that depends on what we already know, what we want to know, and what we're learning. So another way to say this that I believe to be equivalent is if we say X is conditionally independent of Y given Z, you could rephrase that as knowing about Y may give more information about X, but only if we don't already have information from Z. So let's look at an example of a situation where this could occur. You could be traveling away from home, and you have an app on your phone that lets you know there's been an alarm going off at your house, and you also have a news app. And there may or may not have been an earthquake. If you get the notification, hey, your alarm is going off, and you are then asked, do you think there's a news report about an earthquake that you will receive or that exists? This is a question you can ask. if you learn that your alarm is going off, you may be more likely to think, yes, it is more likely than I thought before to see a news report about an earthquake. So you are asked about something and you already have certain knowledge, and then you're asked again. And here, the probability of the news about the earthquake, given that you have an alarm, is likely larger than the probability of the news by itself. So here, under this setup, it would not be the case that these two events are conditionally independent, even though neither directly causes the other. Rather, it's information about one changes our beliefs, our predictions about the other. However, if you were to first get the information that there has been an earthquake from a trusted source that's not the news, and then you are asked, what is the probability that there will be a news report about the earthquake, which would be the probability of news given earthquake recorded in step 2. And then you are asked, and then you get an app notification, says the alarm is going off at your house. So now you're asked about the probability of a news report about the earthquake given both the alarm and the earthquake in step 3. This should not change. If you already have the stronger information that an earthquake has definitely occurred, getting the additional information the alarm is going off doesn't change your probability of expecting the news report. I hope that made sense. That's a quick attempt at explaining the big idea of conditional independence. It actually took me a little bit of time to work through these specific examples to understand it, and realizing that it was not the same thing as a direct cause and effect relationship, but rather it was about what could be reasonably predicted based on the information available. And that changes depending on which information is given in which order. In this scenario, given the earthquake would be Z, and these are conditionally independent if we know about the earthquake. They are not conditionally independent if we don't. So that given information expressed in Z is extremely crucial to the definition.
Yeah, that makes sense. And I think there's a lot of tie-in here with some of the causal inference and causal modeling work. And I know we don't want to go off on a huge tangent. I've been trying to keep myself pinned a bit so we don't go too wide. But Danilo has also done some interesting work on our side, trying to figure out, when we don't know how things are related in terms of their underlying causal graphs, you could even be making hypothesis and comparing data to try to determine what's more likely in a causal graph sense for a set of observed phenomena where you don't actually know the causal graph. Like when we're modeling, we are often building causal graphs, especially when using MAIDs. Like we're saying, suppose things are causally related in a certain way. Then we have real problems where we have observations of phenomena that may or may not be causally related, but you only have the observations of the phenomena. And then lastly, this is particularly interesting when it comes to mixing modeling and data, because you might have some things where you have known causal relationships. You could think of them as like explicitly in your structural model or in your laws of motion. You'll have other things where you might have some incomplete observability or hidden states, and then you might want to reason about what you do and don't know about the causal relationships of the hidden states within your model. So a lot of really interesting things are downstream of this. So even if it might feel a little pedantic from here's a rigorous difference between definitions of similar things, I actually think this is a really important applied concept, and that it comes out when you get down to actually modeling, especially when you're trying to manage problems where you assert some things and you estimate other things within the same modeling environment. But yeah, and I'm also very sensitive to observability as a phenomena, and so the question of what you can observe here, whether you could observe the earthquake or not, is actually affects which of these regimes you're operating in. So in a model with a graph like this, the structure might be the structure, in the sense of the causal links are there, but whether or not you have an observation of the, in this case, the earthquake, the thing that causes both of the others will fundamentally affect what the beliefs you form and what actions you take downstream in the graph. Anyway, end rant.
Well, it's really helpful context for me personally, and I think we are going to touch on some of those things, and it's possible I'm duplicating things that Danilo or others have done in terms of concepts. So we'll see.
Okay, so
That's totally fine. I think
Yeah.
duplicating is not bad. I love seeing things cross-stitched, so I'm really just calling out the cross hooks. It's by no means a complaint.
Maybe I missed a slide, but what is the means of the doctor's value being observed?
So that is a decision that the rule by which that decision is made has to be set somehow. And so right now we're saying this, if we're in the world of Bayesian networks, then it would be a probability distribution based on the tree being sick. Whether or not you set a value for tree doctor in terms of analysis is something that's actually happening at the modeling level.
Okay.
So you basically have to make that assumption or ask that question. It's not it is directly observed by agents within the game, but it also could be set by the modeler as a what if type of question. And here we're basically asking if we already knew whether or not the tree doctor had arrived, and then we found out the tree was sick, would that give any information, additional information about whether or not we believed the patio had been built? And the answer is no, because the tree doctor is in some sense, the tree doctor is first of all not, the tree sick is not visible to Alice. And just in terms of like the path itself, what we're trying to elucidate here is the difference between active and blocked paths, which is a really important property. The active and blocked paths are something to look for and be aware of. And the punchline of the joke, or the heroic ending of the story, is going to be that at some level there are certain properties of this model that are observable only from the graph itself, independent of any probability distribution. So we can know that regardless of what decisions we make as a modeler in terms of assigning specific decision rules or assigning specific probability distributions, some of these things should always have these types of relationships. And so this is very granular what we're doing right now, but it's building up to a high level, very useful conclusion. So in this example, tree doctor blocks tree sick from build patio. And if we knew the value of tree doctor, this would be a blocked path. If we didn't know the value of tree doctor, we would not say it's a blocked path. Similarly, if you just reverse the arrows, the relationship would be symmetric. So here are two of the four things you could look at. And in either case, if you're trying to get from X to Y, and the thing in the middle is informed about, it's Z is blocking from X to Y. So in either of these, it would be a blocked path. So the definition here is we define evidence E, which would be the things that basically we're already taking to be known values. And in this case, we're looking at this middle variable as being part of the evidence, which means it's something whose value we could set or have set. Similarly, if you have this type of scenario, this path is also blocked if Z is in the evidence, because we observe one of these two effects, but we don't know anything about whether the common cause has occurred. It may provide information about the likelihood of the other effect. But if we know for sure that Z happened or did not, then learning about Y doesn't provide an update on X or vice versa. And finally, the one that's sort of the reversed arrows version of that is if you have two potential causes and they could both contribute to an effect, then this is a different condition. The first three were blocked if the middle variable was in the evidence. This one is blocked if the variable is not in the evidence. So we can kind of think about this as a patient has lung disease. Well, two things that could have caused that lung disease are that they smoked or they worked in a factory. If we knowing that the patient has lung disease, I'm kind of struggling with the verbal explanation of this. Let me think about it for just 1 second. Yeah, so here, if you set the value of lung disease and then I'm going to skip it. I'll come back to it. The goal here is to determine how information flows through the graph. And this extends to a more formal definition where you look at longer paths, but it keeps the same idea. And basically what you're looking for is this type of pattern where something down the road of two effects is not in the evidence. So if you have a graph of a Bayesian network and an undirected path in the graph, and then you have a subset of the vertices, which you call the evidence, then you can say the path is active given the evidence if this configuration where two of the vertices feed into a common third never has a vertex here whose it or its descendants escape the evidence, and you don't have any other vertex in the evidence. So if I were actually teaching this as a class, I would, which I'm of course not, we would start drawing these things out and just making sure we understood the property, coming up with examples and counterexamples. It's a useful thing. Maybe I will do it later personally, but it's not in scope of what we're talking about today. So despite the multiple exclamation points that would be exciting, let's move on from the definition, because I want to talk about how this concept is useful if we stipulate that we could in fact recognize these things.
I mean, just going to the point you made earlier about why this stuff is valuable, I'm going to abstract away from the specifics of active and block paths and just say that, being able to extract certain kinds of guarantees or just behavioral properties in general from structure, independent of specifics, is a big part of how you render systems like, I want to say useful. And so like, regardless of which particular technique we're using, if it's a, Bayesian network-based technique or a dynamical systems-based technique, like I think a lot of what we're doing across the board is working in systems with a relatively high degree of uncertainty about individual actions, actors, etc. But we're wanting to be able to make concrete statements of the form, well, if this, then that, or, irrespective of what happens as a result of this thing, we always get that thing type of results. And even if we can't guarantee the ifs on the side of the if then statement, it can be really helpful to understand these often quite complex assemblages by pulling out of them structural properties, sensitivity properties. And I talked about open loop and closed loop behavior because of the control theory stuff, but like ultimately, relationships between the inputs and the outputs, including their sensitivity to the inputs, the output sensitivity to the inputs. And a lot of this for me is the kinds of machinery that give you that for Bayesian networks and MAIDs in particular. And so when we're doing projects, if we're talking about trying to, either develop requirements which call for certain kinds of insensitivities or certain kinds of input-output relationships, and then we're building models in order to try to ask questions like, well, under what circumstances are those requirements met, or how can we ensure those things? The kinds of analytical techniques that you would use for that are things like what Octopus is describing here. So I'm gonna give the floor back, but just trying to like connect it to the like, as always, a kind of engineering process.
Thank you. Because there is actually something really cool that can be said here, which is requires a further definition. So there's all this cognitive front loading, but then it pays off at the end. If you have the evidence that you want to say, okay, I already know these values, and I know the graph of the Bayesian network, the definition is that you say the two sets are directionally separated, given this evidence, if every path between them is blocked. And I would not try to compute this by hand. There are Python packages where you can put in a Bayesian network and ask, are these two things separated? But the big payoff for all this foundation is that you can look at the graph and determine automatically that regardless of how you assign the probabilities, the two things you're looking at are conditionally independent, which is a huge deal in terms of understanding probabilities and modeling, because Dr. Zargham just said that in terms of a modeling process, if I understood what you said correctly, it's about introducing certainty where possible. And this introduces a really big piece of certainty about the model, where you pay the price in terms of computation and understanding at the beginning, but then you know for sure my model should have this property if it's accurately representing the phenomenon that
A
I'm
yes
seeing.
and here is that if you're actually designing a protocol that is mediating behavior of different populations of agents, if you can structure that protocol in such a way that the Bayesian network that represents it actually puts like this directional separation in place. Now, I'm not saying that you can always do that, but you can use that as a design tool. You can say, well, this group of actors facing this set of affordances sets these variables, and this other group of actors with these affordances effectively sets those variables. And if you're designing, structured rules and shared states through which they interact, it's possible that you could design for directional separation of those groups. Now, again, I'm not saying that you can always do it, but I'm just trying to note that like these kinds of analytical techniques, when tied back to engineering design problems, can be non-trivially powerful in keeping your map and your territory close to each other. But you shouldn't assume directional separation. You should like aspire to design the system to have it.
And the good news is that this is very practical, because you can compute directional separation in these types of networks. So, and I mean, like, very practical in the sense that there's Python packages where if you put in the Bayesian network and basically like scikit-learn, but for these types of things. And again, this may be something where other people here or related have already played with it and know about it. It was really exciting to me to think about the fact that you could, from this modeling process perspective, you could input the Bayesian network and check, did I get the directional separation I was hoping for? And additionally, in terms of a model sanity checking, where you've actually assigned probabilities or upgraded to MAIDs and assigned rules, you can do this where you take the MAIDs, you find a way to put it in cadCAD, which produces a data frame. And then after you do that, you fit the data. And then from the data, you can fit the Bayesian network. And you can check and see, does that get the Bayesian network that I would have expected if I just rewrote it by hand to be a Bayesian network? This isn't a perfect check. Like, I wouldn't propose this as any type of test until it had been validated a lot more. But it's an idea of how this might be useful, that it provides, additional levels of certainty surrounding, did I keep everything intact when I added those 5 lines of code, or am I now in a different regime where I'm getting unexpected behavior?
It's a really nice weighted check, like regression test, basically, if you were expecting a property. I was going to note, though, even short of cadCAD models, it seems to me that MSML models might actually be suitable for this kind of check. You would require an interpretation or a view, and Sean could probably speak more to this, but if we interpreted the structural, basically markup of the MSML model as the graph, then you should be able to ask questions about things like the Bayesian this sort of separability of specific decisions. And there's a little bit of markup that Sean's been working on top of the MSML that I think, there's probably a variant of that markup that would support basically direct use of the Python packages. Like with the right markups, with the right interpretation, you'd get the structure of the Bayesian net. And so you could ask and answer questions about properties of those networks that are independent of the specific logics, because they're actually only a function of the dependencies, which is what the MSML already codes. It doesn't have the logic, it just says what depends on what.
Yeah, I mean, it's interesting because I've been thinking from a design perspective a lot about it, like as MSML as maybe even like a Rosetta Stone between different kinds of paradigms or whatever. And the way that one could do that is with like a bridges, like building a bridge where you can take a spec and make it into cadCAD. You might need to add some sort of metadata to different things to make sure it works. But likewise, like leveraging, instead of trying to have MSML do all of the things, have it that it's like, okay, it won't do all the things, but if there is Python packages for specifically having the bridge that says, add this metadata and it can automatically write you out like maybe 90 to 95% of the scaffold of what you need for it to run. So I think it's cool. And like that's where it's like these kinds of ideas of like what bridges would be really useful is what's helpful. So as a side note, if people ever think of kinds of bridges that they would like this, for example, please just drop in the MSML channel, keep trying to like keep track of things that could be spawned out from it.
And then in order to do that, I mean, the natural thing to do would be not to try to make the software do it, but to just try to do the task, like take an existing MSML model that describes the structural relation of a bunch of input-output operations, and then like basically in a Jupyter notebook or something, try to extract from the MSML object the Bayesian network in a format that could be passed into the existing Python tool, and then poke at that to see what it can tell us. And even if it ends up being an entirely manual process, if it's really just a take this object MSML, enrich it with this metadata, run this script to extract the Bayesian network, then use the Bayesian network package to explore, that's like a plenty good starting point. Like you don't need it to be software. And if that pattern becomes sufficiently useful to project teams, that's when you would think about building an adapter or a connector that makes it easier to port from MSML or cadCAD models into a Bayesian network-based kind of structural analysis.
Yeah, no, I mean, I exactly agree with that kind of thought.
So I just wanted to I like this idea of feeding data to create or by using Bayesian networks. Actually, there may not be a single Bayesian network that fits the data, right? There could be multiple ones. But I think that it's pretty cool that, for example, when we create these causal loops or causal diagrams, understanding whether these relationships make sense from data, I think that would be a pretty powerful tool to support that, the model that we have in mind is actually supported by some sort of analytical model, a statistical model that in this case could be a Bayesian network. So yeah, I think it's pretty interesting. I know that in the literature there are multiple ways that you can feed Bayesian networks to data. It could be either with exact methods that sometimes are very complex, but very also rewarding from the point of implementation, and also heuristics, right? That you can kind of have some approximations, sometimes weak guarantees, but it's still useful for very large scale systems. Anyway, this is just to say that I think there is a lot of opportunity at least from my point of view, now I have this idea, but it's that I think that it would be useful to support, the causal loops that sometimes we build to to understand a model.
Yeah, and I like the idea of causal loops as sort of like proto-Bayesian networks. They're not really, because they have the feedback loops in them in a way that I'm not sure fits nicely in the Bayesian network format, but they're a precursor to also just like a more what I'd call a system identification based technique where you have data and you're not just trying to learn some coefficients, you're trying to learn some like literally functions. Like learn the structure from the data. And there's always a trade-off between how much weight you put on the structure, the structural model, versus how much weight you put on the black boxes or the places where you have, universal approximators, whether they're neural networks or, radial basis functions or whatever. You end up, and I think, at least for me, this is the takeaway with all these modeling tools is that in practice, we're going to use a mixture, and a lot of the systems we work with are going to have both explicitly asserted causal relationships and like implicitly potentially learned from data causal type relationships, and that in practice we're going to need to work with both. And I always fall back on the robotics literature since it's what I know best. And we almost always have good first principle models of things like physics, but then of course the real world is messy and we don't know all the masses and spring coefficients and whatnot. Plus the spring model is always already an approximation. And so you get this, you get a plant model, you get a error, a nonlinear error model, you get some sort of external environmental behavioral stuff that you really don't know at all. And so you end up with this mixture of things that you know really well to things you know nothing about, and you still want some, ability to make claims about closed loop behavior, right? And again, for me, that's what this really comes down to with these systems, is that they get embedded in the world. The world is always going to have things that we can't totally model and shouldn't assume our models are complete, but then somehow we need to be able to assert behavioral properties that are sticky over time. And so the figuring out what are those constraints and how do we achieve them and how do we identify the circumstances under which they fail, despite this tension between parts of our model, which we're literally designing and we have direct control over and total observability over, to stuff in the middle, to stuff that we have like at best proxy metrics for and is going to emerge in response to the behavior of the system, both what we designed and the behaviors of other actors. And handling that continuum means necessarily being kind of multi-scale, multi-modeling regime. And so we're going to continue to have these explorations about all of these different modeling tools and techniques, because our goal is to steward projects all the way from their kind of ideation, conceptualization, what if it worked like this, all the way to having things that are kind of in production, being monitored, potentially being steered through some measure of policy making, that which is under control of its operators. And then in complement to the things that are out of the control of those operators that emerge in response to those operators' policy decisions.
So I think that I'm just going to give an ad for this next session. The big idea, I'm going to come back to this later. Maybe we can discuss this offline, is questions about like what a functor between GDSs and MAIDs might look like if such a thing is definable. But the big question that I want to get to in the next session, the big idea from Bayesian networks was information flow and recognizing information dependencies in terms of updating beliefs. The big thing that MAIDs add that is not inherent in Bayesian networks is the idea of a strategy, that agents are taking actions and that you can adjust. And so what I hope to actually build a proof of concept for next time is a translation layer here that would enable us to do quick what-if experiments over different strategies so that you can easily compare, well, what if Alice is malicious? What if Alice is strategic? And again, the setup in terms of cognitive structural work ahead of time hopefully pays off later when we know more things for sure. So next time I want to talk about strategies in MAIDs and strategies in cadCAD and how those might be helpful, why those might be worth paying the cost of additional work up front for more information quicker at an intermediate point.
Makes sense. Thanks for the time today. We're a few minutes over. I hope everybody enjoyed it. It's recorded for the folks who aren't on. And I think there's some interesting overlaps between your last comment and some work that David Sisson has been doing around definitions of data and like data processing and distinguishing between, say, things like information and knowledge and understanding. And at least for my part, I've coded in my head some of that as the difference between sort of more, let's just call it like facty stuff, like, hey, the state of the world is this. As you move down the pipeline, you get to something more like a system identification, where you have a more complex, often more tacit understanding of how something works that you can use to take decisions. But like that is a much more complex, entangled, and has knowledge of explicit and data and like dynamics. And again, that's very much I'm thinking of it more as human as a cognitive actor there. But, you know, when we think about it from an engineering perspective, like, you know, are we moving from, you know, facts in a database, like a collection of input data points, or, you know, an integrated database with some statistics over periods of time, up to these kind of, you know, more advanced, like, hey, we have a deeper, more structural, more kind of, you know, system ID'd model of the world, accounting for both, you know, for more and more of this stuff. And as we get further down that path from raw source data up to kind of a more holistic understanding of the dynamics of a decision context, I think we necessarily have a more multifaceted, or arguably a sort of ensembled model of the world, where part of the understanding is knowing, the more tacit understanding is knowing which machinery to use pursuant to which decision context. So a plug for David's forthcoming work, which I think he'll also be circulating around for feedback internally in not too long.
Was really good. Thanks so much.
Nice. Yeah. Thanks, Octopus. That was great. Thanks, everybody.
Yeah, that's great. Thanks, Octopus.
See you guys.
Bye-bye.
Bye.
Bye. Thanks again.
Thank you. Thank you so much.
It's been fun. I'm really glad that we're doing this. I think we should, well, I'll give you the time to keep working through it, but as we're wrapping it up, we should talk about some more and try to figure out other things, because I think it's really helpful for just working through this stuff. It's just too easy to kind of use it on the fly and not necessarily reintegrate and, like, you know, I guess I want to say, like, grok what you're doing. Sometimes when you're doing projects, it's really easy to get caught up in, oh, these are the things we need to do, but it's a separate channel for, why did we do that? What is that good at? Should we do it the same way next time? And holding, you know, those loops in parallel, I think, is helpful, because you can't really do it in the project, as you've noticed. Like, you have deadlines, you've got timelines, you've got deliverables, but then, like, just because you can't do it in the flow of a project doesn't mean you shouldn't do it. And so I'm seeing this as a really successful pilot into, you know, where and how we do the foundations and methods, kind of, you know, sense making.
Thank you so much. I really appreciate the opportunity. And I've had a lot of fun learning this cool new stuff in different ways, and excited to do more.
Cool. Thanks.
I
Have a
think.
good one. Bye-bye.